Picture this. You're trying to dock a massive, heavy vessel in a crowded marina. The wind is howling, the current is pushing against you, and your main engine can really only move you forward or backward. You need lateral magic. You need a bow thruster.
Yeah, it really is the ultimate difference between a stressful, potentially disastrous docking experience and, well, a masterclass in precision control.
Right, because without that lateral thrust, you're entirely at the mercy of the elements the very second your forward momentum stops.
Exactly. You're basically just drifting.
So today we are doing a deep dive into the anatomy, the extraction, and the meticulous maintenance of side power bow thrusters.
Sounds intense.
It is. We're pulling insights from a really comprehensive marine guide by Yacht Supply 24. We are going to equip you with the knowledge of what makes these systems tick, why they are the secret weapon of tight maneuvers, and how to safely disassemble and reinstall them.
Without sinking the ship.
Figuratively or literally. But before we get into the heavy lifting of, pulling this machinery out of a hull, we need to understand what it's actually doing down there in the dark water.
Right. So at its core, a bow thruster is an electric motor and a propeller hub. It's embedded in a tunnel that cuts straight through the forward section of the ship's hull.
And its sole objective is pushing water laterally, right?
Exactly. By shooting a jet of water out of the left or right side of the bow, it physically shifts the nose of the boat in the opposite direction.
I like to think of it as trying to parallel park a massive bus, but suddenly you have a set of, shopping cart wheels that let you slide perfectly sideways.
That is a surprisingly accurate analogy. And while you often see bow thrusters on large yachts to help with port-side handling and tight berths, you also have stern thrusters positioned aft to shift the tail.
Right, so integrate both, and you achieve 360-degree control without ever needing a tow from a tugboat.
Yep, total independence.
But, I understand the convenience, but it raises a fundamental question for me. The boat's main engine is already incredibly powerful. Why do we need to rely on entirely separate electric motors just for low-speed maneuvers? Why can't we just turn the wheel and use the rudder?
Well, it really comes down to fluid dynamics.
Fluid dynamics, yeah.
To steer a vessel with a rudder, you require forward momentum. A rudder is essentially an underwater wing.
Oh, right, because it only generates turning force when water is flowing quickly over its surface.
Exactly. If you are idling in a crowded harbor, barely creeping forward, you simply don't have enough water passing over that rudder to pivot a heavy hull.
Especially if a crosswind is hitting the side of the boat.
Right, so the main engines are built for open water speed, completely lacking lateral finesse. They are basically useless for steering at 0 speed.
And that is where the specific engineering of a bow thruster takes over.
Yeah. When you push the joystick at the helm, a signal is sent to a component called the solenoid.
Right, the solenoid.
Think of it as a heavy-duty electromagnetic switch. Regular switches would just melt under the immense electrical load required by the thruster.
Because we're talking about high-amperage direct current here.
Huge amounts of power. The solenoid safely bridges that connection, instantly allowing all that power to flow from the battery banks to the electric motor.
And to get that electricity into the spinning part of the motor, the system uses carbon brushes.
Yes, because the electricity needs a way to cross from the stationary part of the motor into the spinning rotor.
You can't just wire it directly, right?
No, the wires would twist and snap instantly. So you have these blocks of carbon, the brushes, that are physically pushed against a spinning copper cylinder on the rotor.
That's called the commutator, right?
Exactly. The carbon conducts the electricity while allowing the motor to spin freely. It delivers pure, sideways, brute force precisely when you need it.
But knowing that this brute force relies on an incredibly sensitive mix of high-voltage electricity and delicate moving parts, it creates a massive problem when it's time for maintenance.
Oh, definitely. You can't just take a hammer to something submerged in salt water.
Right, you have to isolate the environment. And the absolute first step, before you even touch a wrench, is shutting off the main power.
It's non-negotiable. You are dealing with high-amperage direct current power in a wet, highly conductive environment.
Yet, failing to isolate the power doesn't just risk damaging the thruster, it is a lethal hazard.
A massive hazard. Once the power is physically disconnected and locked out, then you can start looking at the specific toolkit required.
And you definitely aren't just grabbing a standard household toolbox for this.
No, you need Allen wrenches for precision work, specialized screwdrivers, anti-fouling brushes to clean off marine growth.
But two tools really stood out to me in the manual: bolt extractors, and seal tools.
Yeah, those are lifesavers.
Why do you need such specialized gear just to take a motor off a mount?
Well, marine environments basically fuse metal together over time. Salt water causes threads to calcify.
Could they just get stuck?
Totally stuck. When you try to back out a steel bolt from an aluminum housing, the head of the bolt will often snap clean off.
Oh, man. Leaving the threaded shaft trapped inside the hole.
Exactly. A bolt extractor allows you to drill into that broken shaft, bite into the metal in reverse, and slowly back it out without destroying the expensive housing.
That makes sense. And the seal tools.
They are vital because the only thing keeping the ocean out of the boat is a series of delicate rubber O-rings.
And if you just use a flathead screwdriver to pry a seal out.
You will scratch the metal seating instantly. Even a microscopic scratch will allow pressurized seawater to bypass the new seal later.
Wow. Okay, that makes the pre-op checks make a lot more sense. It sounds like we are prepping for open heart surgery on this boat.
It really is. You have to physically test the control panel, ensure the cable connections are perfectly intact, check the fuses, and record every single finding.
But one of the major checks mentioned in the guide is monitoring the system for carbon dust levels.
Yes, that is a big one.
If this motor is in a sealed environment, where is this dust coming from?
It comes back to those carbon brushes we discussed earlier. They are constantly pressing against the spinning copper commutator.
Right, to conduct electricity.
Exactly. That constant physical contact creates intense friction. Over time, the solid carbon blocks slowly wear down, shedding a fine, highly conductive dust inside the motor housing.
Okay, so it's a bit like the dark brake dust that builds up on the wheels of your car from the friction of stopping.
That is a perfect parallel. But inside an electric motor, that dust is trapped.
And since it's conductive, that sounds bad.
Very bad. If it builds up too heavily, it can coat the internal components and actually bridge the electrical gaps between the copper contacts.
Causing a short circuit?
Worse, it causes the electricity to arc, literally jumping through the air. That creates massive heat, shorts out the motor, or causes a total system failure.
Wow. So checking the dust levels early is crucial.
Absolutely. Excessive dust is the motor's physical way of warning you that the brushes are wearing dangerously thin.
The other pre-op check that really fascinated me is inspecting the state of the zinc anode.
Ah, the zinc anode. It is the ultimate sacrificial component.
Its entire engineered purpose is to die so the rest of the machinery can survive.
Yeah, that's exactly what it does.
But how exactly does a chunk of zinc protect an entire mechanical propulsion system?
It relies on the galvanic scale of metals.
Okay, break that down for me.
Well, when you submerge different metals near each other in a conductive fluid, like a bronze propeller, a stainless steel drive shaft, and an aluminum housing sitting in the ocean,
Right.
you unintentionally create a giant low-voltage battery. The salt water acts as an electrolyte.
Oh, wow.
Yeah, so an electrical current begins flowing between the metals, literally stripping electrons from the less noble or weaker metal.
Meaning that stripped metal begins to rapidly corrode and disintegrate into the water?
Exactly.
So the ocean itself is actively trying to dissolve the metal housing of your expensive thruster.
It is an inevitable chemical reaction. So to stop the ocean from eating the stainless steel and bronze, engineers bolt a chunk of zinc to the underwater assembly.
Because zinc is highly active on the galvanic scale.
Right. It is much weaker than the other metals. The corrosive electrical current attacks the zinc first, pulling electrons from it while entirely ignoring the critical thruster components.
So the zinc dissolves over time, taking all the damage.
Yep. If you do your pre-op check and see the anode is completely eaten away, it means your precision-machined thruster is now next in line to be dissolved by the ocean.
Good to know. Okay, so with the power completely isolated, the dust checked, the tools laid out, it's time for the physical extraction.
The fun part.
Right. You start by disconnecting the heavy gauge wiring. The manual really stresses using insulated tools, loosening fasteners gradually, and meticulously labeling every single wire to avoid crossing them later.
Labeling these heavy gauge wires is so important. It's less about keeping things neat and more about preventing a catastrophic electrical bridge later.
It sounds exactly like a bomb disposal scene in a movie. Cut the blue wire or the red one.
Pretty much. But there is also a massive warning in the guide: do not bend the wires.
Right, why is that?
The warning against bending them is purely mechanical. These cables carry massive current. If you sharply bend thick copper marine wiring, You create microfractures in the individual copper strands inside the insulation.
It's exactly like bending a paperclip back and forth, isn't it? It creates a localized hot spot of friction until the metal finally snaps.
Exactly. And in a marine electrical system, that hotspot creates severe electrical resistance. The current struggles to push through the fractured strands, generating immense heat.
So a sharply bent wire can quite literally become a hidden fire hazard deep inside the hull of the boat.
Precisely.
Okay, so once the wiring is safely out of the way, you move to removing the motor assembly and the tunnel gear. You detach the mounting brackets, heavily supporting the weight so it doesn't drop.
You definitely don't want to drop it.
And then you have to detach the propeller outside the hull. You hold the thruster steady, loosen the front fittings, twist the parts free slowly, and pull the components apart gently.
Gently being the key word there.
But I have to push back here. If I'm working under a hull and a marine part is completely crusted over with salt and calcification, my immediate instinct isn't to be gentle.
I know it's tempting.
Right. My instinct is to grab a longer breaker bar for leverage and just yank it until it breaks free. Why is there such a strong emphasis on twisting slowly and soaking it in penetrating oil instead of just using brute force?
Because yanking is the exact moment a routine maintenance task turns into a catastrophic multi-thousand-dollar nightmare.
Really, just from yanking a wrench.
Think about what you are actually pulling against when you yank that wrench. You aren't just fighting a stuck bolt. You are applying torque against the delicate internal drive shafts and the highly sensitive rubber waterproof seals sitting behind that propeller.
Ah, so the risk isn't just snapping the external bolt. The risk is breaking the physical barrier that keeps the ocean out of the inside of the boat.
Exactly. If you force a salt-welded component, the torque can warp the main stainless steel drive shaft by a fraction of a millimeter.
Which doesn't sound like much.
It's tiny, but that microscopic bend will cause the propeller to vibrate violently when it spins at high speed, eventually tearing the waterproof seals to shreds.
Oh, man.
Or you snap the bolt off inside the housing, trapping a piece of broken steel inside a precision-machined threaded hole.
Which means drilling it out.
Right. By using penetrating oil to chemically break down the salt bonds, cleaning the threads meticulously, and twisting slowly, you are respecting the tight tolerances of the machinery. Patience preserves the equipment.
Okay, so let's say you've successfully wrestled the thruster out. You used the penetrating oil, you were patient, and you didn't warp the drive shaft.
Good job.
Thanks. We pull the unit out of the boat. But marine environments are brutal, so before this goes into storage or gets rebuilt, we must hunt for invisible wear and tear.
Right. We are essentially performing a mechanical autopsy.
And the handling instructions during this phase prioritize the preservation of the removed unit. You lift it onto a padded surface. You wipe off all excess salt water immediately.
That's to halt the galvanic corrosion we discussed earlier.
Got it. And you are instructed to store it in a cool, dry spot away from direct heat. Now, I understand drying it off, but why does the temperature of the storage spot matter so much?
It's actually really interesting. It has to do with the thermodynamics of sealed housings.
Thermodynamics. For a marine thruster meant to operate in freezing ocean currents or tropical waters, why does it need a cool spot in the garage?
Because the lower gear leg of the thruster is completely waterproof and it's filled with lubricating oil.
Right.
If you place that sealed unit in direct sunlight or next to a heavy heat source, the air and fluids inside will expand. That puts massive pressure on the rubber seals from the inside out.
Oh, I see.
And when it cools down again at night, the internal pressure drops, potentially sucking humid outside air past the stressed seals.
And then that humidity condenses into water droplets inside the housing.
Exactly, silently rusting the internal gears while it just sits on a shelf.
That is fascinating.
Yeah.
So the autopsy phase then moves into the physical inspection. You are actively hunting for tiny cracks in the frame, feeling the metal surfaces for any roughness, testing the mechanical joints by hand, measuring the worn parts against the manufacturer's original tolerances.
And looking for discoloration, that's a big one.
Yeah, the guide specifically mentions looking for discoloration on the metal parts. What exactly is a change in color telling us? Is it just a cosmetic stain from the water? Or a red flag for something worse?
Well, if this heavy-duty metal machinery is submerged in the ocean is a great coolant for the external housing. But the electric motor itself sits entirely inside the dry hull of the boat, above the waterline.
So it isn't submerged at all.
Right. And even the lower gear leg, which is underwater, is a sealed unit. If you see discoloration, like a bluish tint on the metal, similar to what you'd see on a motorcycle exhaust pipe.
Yeah, I know that look.
or dark scorch marks around the electrical terminals, it is a massive red flag.
Because it means the part generated heat faster than the surrounding environment could dissipate it.
Exactly. It is physical evidence of intense electrical arcing or severe mechanical friction. Extreme heat fundamentally changes the molecular temper of the metal,
Making it weaker.
significantly weaker, more brittle, and highly prone to snapping under load.
So even if the part looks whole and doesn't have a visible crack, that blued metal is a ticking time bomb.
Completely. Reinstalling it means risking a total system failure right when you're trying to dock in heavy winds. The autopsy phase is your absolute best chance to catch these heat signatures.
Okay, we've performed the autopsy, we've cleaned the housing, replaced the worn carbon brushes, swapped out the dissolved zinc anode for a fresh one, and discarded any heat-damaged metal.
Everything is prepped.
Now comes the reinstallation. We have to put the thruster back into the hull so it actually survives the ocean again.
Right. Preparation for reinstallation involves verifying your power requirements against the ship's battery banks. But the most critical physical step is the alignment.
You have to position the tunnel securely, and the guide specifies using precision-level tools to ensure a perfectly straight alignment before you tighten the mounting bolts evenly.
Alignment is everything here.
But why does a slight misalignment matter so much? I mean, if the propeller is spinning inside a giant tube of water, does a millimeter or two off-center really impact the performance?
Oh, it drastically impacts the hydrodynamics. The clearance between the spinning propeller blades and the inside wall of the tunnel is incredibly tight,
Like, how tight?
often just a few millimeters.
Good.
If the motor is bolted down slightly misaligned, the blades will physically scrape against the inside of the tunnel.
Yikes. That sounds bad.
It is. And even if they don't touch, an off-center propeller creates unequal water pressure, leading to cavitation. Yeah, the water literally boils at the low-pressure edges of the blade, creating air bubbles that collapse with enough force to slowly pit and destroy the metal prop.
Wow. Which makes the moment of truth so critical. You've aligned it, bolted it down, and now you run the test.
The final test run.
You power up the system, push the joystick forward, and you are supposed to listen for a smooth hum.
That smooth hum is what you want to hear.
It reminds me of a musician tuning an instrument. You just inherently know when the machine is singing in harmony.
That's a great way to put it. You check the lateral motion on the port side, throw it in reverse, and observe again.
You're feeling the hull for steady pull and monitoring for heat buildup. But let's say I power it up, and instead of a smooth hum, I immediately hear an awful grinding noise. Is the whole unit ruined? Or what is the immediate first step according to the manual?
Your immediate first step is cutting the power instantly. Do not attempt to push through it.
So shut it down right away.
Yes. A grinding noise points to exactly what we just discussed. Poor alignment causing the blades to scrape, or an obstruction in the propeller hub.
Like a rogue piece of heavy fishing line, or marine debris could have been sucked in.
Exactly. You shut it down, you pull the assembly back out, and you recheck your alignment measurements or clear the hub.
You never force the system to correct itself.
Never. Preventative maintenance is about physically balancing the unit and checking for vibrations by hand, so you never reach the point of a grinding noise in the first place.
Well, we've brought the journey full circle. A side power bow thruster isn't just an electric motor bolted to the bottom of a boat. It's a meticulously balanced corrosion-fighting ecosystem.
It really is.
From the electrical transmission of the carbon brushes to the thermodynamic realities of sealed housings and the hydrodynamics of propeller alignment, it is a highly engineered machine that gives you ultimate lateral control in the tightest, most stressful docking situations.
Absolutely. When you understand the extreme patience required to extract these components without warping a drive shaft and the rigorous demands of surviving a galvanic saltwater environment, it shifts your perspective entirely. You have to work with the physics of the environment, not against it.
You really do. You now know exactly what it takes to master the lateral movement of a massive vessel. But before we wrap up, consider the concept of the sacrificial zinc anode we discussed.
That component engineered purely to be destroyed by the environment so that the core system survives.
Exactly. It makes you wonder, where else in our modern engineering or even in the structures of our daily lives do we install sacrificial systems just to absorb the damage meant for us? Take a moment to think about what the anodes are in your own world.